Think about this. The tissue in your hand may weigh almost nothing, yet a modern factory can turn millions of kilograms of raw fiber into it every year. What looks like a simple, soft sheet actually passes through pulpers, pumps, screens, forming fabrics, giant drying cylinders, razor-sharp doctor blades, and computer-controlled inspection systems. And here's what nobody tells you. The final softness comes from a process that moves faster than a car on a highway. Today, you're going inside that process, from forest fiber and recycled paper all the way to the finished tissue roll sitting on a store shelf. Most people never think about this, but tissue begins with something much rougher than the finished product: fiber. Depending on the grade and mill, manufacturers can use freshwood pulp, recycled fiber, or a combination of both. Fresh fiber often comes from managed forests, while recycled fiber can begin as recovered paper collected hundreds or even thousands of kilometers away. The strange part is that before this material becomes soft enough for your face or hands, engineers must first make millions of individual fibers behave exactly the way they want. For virgin tissue, the journey can begin in northern forests where spruce, pine, birch, and other managed tree species supply the fiber. A tree does not simply become tissue. Mills first turn wood into chips, then separate the cellulose fibers through pulping and bleaching. The exact supply chain varies by manufacturer and region, so there is no single mine, farm, or forest that supplies the entire tissue industry. In one example, Metza Tissue reports that about 70% of its tissue uses fresh fiber and that more than 95% of its pulp is certified, with origins traceable through its supply chain. At the mill, giant machines strip and chip the wood into small pieces that look nothing like paper. The chips enter a chemical pulping system where heat and alkaline chemistry break down the material surrounding the cellulose fibers. Recycled fiber follows a different path, because old paper may contain inks, coatings, adhesives, and other contaminants that the mill must remove. That difference matters. Some recycled fiber systems can lose a substantial portion of the incoming material during cleaning and de-inking, while virgin pulp arrives with a much more consistent fiber structure. The pulp then goes through cleaning, screening, and, when required, bleaching. Engineers use carefully controlled chemistry to remove unwanted color and contaminants while preserving the fiber properties that tissue needs. Hydrogen peroxide, sodium hydroxide, chlorine dioxide-based systems, and other chemicals can appear in different pulp and bleaching operations, but the recipe depends heavily on the fiber source and mill design. By this stage, the rough raw material is transformed into a pale suspension of microscopic cellulose fibers floating in mostly water, and that watery mixture is about to become paper at astonishing speed. But here's the first hidden trick. Tissue needs enormous quantities of water because the fibers must travel through the machine as a dilute suspension before they form a sheet. The water does not simply disappear afterward. Modern mills continuously collect, clean, filter, and reuse processed water wherever the system allows. Energy and water therefore become two of the biggest engineering challenges in tissue production. And when you realize that the finished tissue can contain only a tiny fraction of its original processed water, the next stage suddenly looks less like papermaking and more like controlled water removal on an industrial scale. Now the real transformation begins. The diluted pulp travels through an approach flow system that carefully controls fiber concentration, pressure, flow, and cleanliness before it reaches a head box. The machine spreads a suspension across a forming section, where water drains rapidly through a moving fabric while the fibers remain behind. Modern tissue machines commonly operate around 1,200 to 2,000 meters per minute, with some designs reaching roughly 2,400 meters per minute. So the sheet formed while the entire machine is moving at breathtaking speed. Imagine standing beside that forming section. You hear pumps roaring, rolls spinning, water rushing, and air moving through the machine. The sheet may contain only a small amount of fiber compared with water, yet within seconds a machine has transformed the suspension into a continuous wet web. Suction systems and forming fabrics help remove water while preserving a uniform fiber distribution across the machine width. This stage demands extraordinary control because a tiny disturbance can create a weak spot that later becomes a devastating web break. Next comes pressing and transfer. The wet web moves on a felt toward the press nip, where controlled mechanical force removes additional water and helps transfer the fragile sheet onto the heated Yankee dryer. The exact pressure depends on the machine, roll design, furnish, and tissue grade, so engineers tune the nip rather than follow one universal number. What matters is balance. Remove enough water to reduce the drying load, but avoid crushing the structure that gives tissue its softness and bulk. And this is where it gets truly extraordinary. The Yankee dryer does a job of a gigantic industrial heater and a precision surface at the same time. The wet tissue adheres to its polished cylindrical surface and rapidly loses moisture as the drum turns. Depending on the design, steam inside the Yankee can heat the shell into roughly the 130 to 180 degrees Celsius range, while hot air hoods above the sheet can operate around 300 to 550 degrees Celsius. The sheet can move from roughly 40% dryness to more than 90% dryness in a remarkably short time. The sheet now reaches a moment that makes tissue feel like tissue. A thin creping adhesive layer helps control how the web grips the Yankee surface, and a precisely positioned doctor blade strikes the dried sheet from the cylinder. Instead of leaving as one smooth film, the sheet buckles into microscopic folds called crepes. Those folds increase bulk, softness, and stretch, turning a thin sheet into something that feels dramatically thicker between your fingers. The machine does this while the Yankee can race at roughly 1,200 to more than 2,000 meters per minute. What happens next surprises even experienced engineers when you see it for the first time. A sheet that looks almost impossibly fragile emerges from a machine moving faster than a kilometer every 30 seconds. The crepe web flies toward the reel, where the machine winds it into a huge parent roll. One modern tissue line can produce tens or even hundreds of tons per day depending on its width, grade, speed, and configuration. The giant roll looks finished, but it is still far too large for a supermarket shelf. And the most delicate part of the journey has not ended yet. Before anyone turns that parent roll into toilet tissue, napkins, facial tissues, or kitchen towels, engineers inspect the web continuously. Cameras and sensors can monitor basis weight, moisture, formation, wrinkles, holes, streaks, dirt, and other visible defects while the sheet moves at extreme speed. Online inspection systems can synchronize multiple high-speed cameras and track process disturbances with very fine timing, helping engineers locate where a defect began instead of simply discovering the problem at the end. The converting department now takes over. Giant parent rolls unwind through machines that may slit the web into narrower lanes, laminate plies, emboss patterns, fold sheets, or win smaller rolls depending on the product. For toilet tissue, the machine can create perforations at controlled intervals so the consumer can tear one section cleanly from the next. For facial tissue, high-speed folders create interlocking sheets that rise from a box one after another. The machinery looks calm from a distance, but close up, hundreds of synchronized movements happen every second. But machines cannot judge everything by numbers alone. A sensor may detect a variation in thickness, while an experienced operator notices a subtle change in sound, vibration, sheet behavior, or the feel of the finished product. That human judgment can save an entire production run when a tiny mechanical or fiber problem appears before the automated system fully understands it. Tissue may be engineered at microscopic scale, but the final question remains surprisingly human. Does the sheet actually feel right? Quality control also includes physical testing in the laboratory. Technicians can measure basis weight in grams per square meter, tensile strength, stretch, absorbency, thickness, softness-related properties, moisture, and other grade-specific characteristics. Tissue grades often sit in a very light range, commonly around 13 to 30 grams per square meter, although product can fall outside that range. A sheet can look perfect and still fail if its strength, absorbency, moisture, or structure misses the mill's target. Now zoom out from one factory to the entire world. Depending on the exact product definition, industry datasets put global tissue-related production in different categories, but one major 2024 dataset estimates about 75 million tons of toilet or facial tissue stock, towel, and similar paper, with production valued around $115.5 billion at estimated export prices. Another broader category that includes toilet paper, napkins, towels, and tissue stock reaches well above 130 million tons. The difference comes from what researchers include in the definition, but either way, the scale is enormous. China stands at the top of the production map, followed by the United States and India. One 2024 estimate places their tissue stock production at roughly 15 million tons for China, 8.9 million tons for the United States, and 5.8 million tons for India, together about 43% of the global total in that category. Other major producers include countries such as Pakistan, Japan, Brazil, Nigeria, Indonesia, Russia, and Mexico. So the next tissue sheet you use may represent a supply chain crossing forests, mills, ports, warehouses, and factories on more than one continent. Did you know the United States ranks among the highest tissue consumers per person, with one 2024 estimate putting consumption around 27 kilograms per person, while Japan reached about 23 kilograms. Did you know global tissue stock imports alone reached roughly 3.5 million tons in 2024, showing how much product crosses borders before reaching consumers? And here's another surprise. Some modern tissue machines run around 2,000 meters per minute, meaning the paper web can travel more than 33 meters every second while engineers control its formation, moisture, drying, creping, and tension. Over the last 50 years, tissue manufacturing has changed from relatively mechanical papermaking into a highly automated science of fiber, heat, airflow, chemistry, sensors, and control software. Machines became wider and faster, forming technology became more precise, energy systems became more efficient, and online inspection moved from occasional checking toward continuous monitoring. The future will likely push further toward lower energy consumption, smarter water recovery, more recycled and responsibly sourced fiber, and machines that adjust themselves in real time. Current market forecasts vary widely because analysts define the tissue market differently, but major forecasts still point toward continued growth through the 2030s. So think about the journey one final time. A tree or recovered sheet becomes fiber. Fiber becomes a watery suspension. That suspension becomes a microscopic web. And the web races across a heated Yankee cylinder before a doctor blade gives it the softness and stretch we recognize. From there, cameras inspect it, machines cut and fold it, laboratories test it, and logistics networks move it toward homes, hotels, hospitals, restaurants, and stores. What looks like the simplest paper product in your home may actually be the final result of thousands of carefully controlled decisions made in fractions a second. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.